It's Wednesday again. Do you have any questions? Giselle, Madison, do you guys have any questions?
Yes, I do. It's not regarding the quiz or anything. It's regarding like my attendance on Monday. It said I got counted 0 for attendance, but I think I just got in class like 10 minutes late.
Oh, okay. Yeah, I think I probably relied on
Yeah.
Okay, it's Monday, right? This Monday. Yeah, let's make a note so I can change it right after class or change the attendance for.
Thank you.
Any other questions? Because today is Wednesday, we're supposed to have a quiz over 5758. Do you have any question over the 5758? No question? All right, if there's no questions, I'll hand you the quiz question. So Giselle, are you going to take the quiz online?
Yes, ma'am.
Yes, ma'am. That's fine. Thank you. You can use your computer because we are going to use the normal distribution table. You can pull up the normal distribution table on your computer. Let me pull up the question. Drive. Wonder if there are other ways to go to the drive. I always go through. Today's quiz 3. This is a quiz 3 question. There's 2 of the one question from 5-7, one question from 5-8. 5-7 was approximation using normal distribution to approximate binomial distribution or sum distribution. 5-8 was the Chebyshev inequality. Those are the quiz questions. Yeah. Hi, Anthony. Let me post the Dropbox for the quiz and the place for you to submit your motion. When you are scanning your answer that you write out, make sure you have all your answers on the page, because for quiz 2, Giselle, when you're uploading, I think one of the number was cut off halfway. Make sure you have the whole thing. You can also submit multiple pages just to include everything on your paper. I was able to grade it, but I see some of the edges was cut off. The calculation was cut off. After you submit it, I think you can see your submission for the whole page is in image. Yes. I think for the same question, I have slightly different answer. So this is really the mean portion, right? So this minus 1, 2 should be if this when n is large enough, the proportion goes to 2. But the 0.04, I choose a really small number. This is an epsilon, right? So according to Chebyshev, it should provide this is less than, it's bigger than. So then,
Yeah.
yes, this is bigger than, that is what you need to calculate. But there's no k in 0.04. So you kind of have to figure out the k. So this was 0, right? I see. You got the same number, okay. Maybe my process is different.
Isn't this supposed to be K's times standard deviation, right?
Yes, that's k times standard deviation, yes.
So then down here I did the K.
So you calculate k. So you first find the standard deviation and you figure out what you're supposed to do. Yeah, see, interesting. That's it. But we should have similar answer. I went over the other one way around. I was in the section we have like t y over n minus p, y over n minus p probably is less than. Thinking the book was the bigger than, so it has a different inequality, but the value is similar. I think in the textbook we also have this.
Yes, yes.
So this way you can choose different n and have the boundary calculated. Let me see if we got all the same. The first one is the same, and then this one minus, and then the second one was this. Okay, so that's that lower bound. I think you have the same. The last one we switch to 1,000. This was 1,000. So it should be this lower bound. That's cool. Even though we choose different approach, we're not having the same answer. Thank you. Will you guys finish? Giselle, Madison, Anthony, are you almost done?
I'm almost done. I'm on part B of the second one, but I'm a little confused because, like, on the second one, part A, I found the standard deviation, and I got like my number, and then I squared it. But like for some reason, I keep getting 1 for like whenever I plug it into my formula, I get 1. That can't be an answer, right? Like it has to be like a decimal form.
No, it's possible sometimes the value is at the boundary. I mean, the probability could equal 1 or 0.
Okay.
We're trying to find a lower bound for the probability, so it's possible for it to be a small or bigger number.
Okay.
Madison, are you finished? Anthony? I already see submissions, I'm not sure. It's already submitted. Thank you. See. That's the quiz for today. Today we're gonna continue with section 6.3. Do you have any question for 6.2 or 6.1? Okay. Let me see. Giselle, have you submitted it yet?
I'm on the last question.
Okay.
On part C.
So do you finish?
I'm almost there. I'm so sorry.
I'm still waiting for submission. Let me just start with what we were talking about today. Let's try to finish section 6.3. The title is called Order Statistics. So the name sounds like a different type of statistics. Actually, it is a special name that we call the data set when the data set is already ordered. And we started talking about last Monday, we started talking about it. The definition for order statistics, suppose you have a random sample of size n. So here you have n numbers selected from the same distribution. Now, order statistic is when you put all the random variables in order from small to big. And now you have a rank. The y1 representing the one that's the smallest in the entire data set. Y2 is the second number, and then yn would be the highest value in the data set. All right, so that gives us it's kind of like from one vector to another vector. If you consider all the x value, you have n x value. If you consider that as a vector, then y1, y2 to yn is another vector, which contains the same number, same value number, but just different order. Which is why we're naming this order statistic. Statistic is information that we selected out of the population. Statistic is information that we can calculate out of a sample. So here the X value are the sample, but we put them in order, and then that made it possible for us to do a lot of study. So this section focuses on one thing, that is, suppose that R's number, R being any number from 1 to n, YR representing the rank R in the Y values, Y value, and we want to figure out if we can know more about YR, and then YR can be Y1, Y2, Y3, or Y4. So how do we know the distribution of YR? And then we're using this example as a way to look at the behavior of Y4. For example, let's just randomly pose a probability question. Let's say we're going to calculate probability Y4 is less than 1/2. And that was a question we started talking about last time. And we figured out that we could calculate the probability for X to be less than 1/2. That is, all you have to do is to calculate the integration of the density function toward the probability of an individual value to be less than any given number. What we can do is calculate. We did start talking about it last time, that if you want to find out what is the probability that X is less than 1/2, this is something we already talked about. The probability for the X value to be less than 1/2. What you can do, you can calculate, this is something we went over last semester, that this probability is the integration of your density functions. We end up have to integrate from 0 to 1/2. We integrate the density function to X, dx, and then obviously the antiderivative is X squared. And you're going to put in the upper limit and lower limit for the integration, and you get 1/4. So we have this question like, what is the probability Y4 will be less than 1/2? Is it the same as the probability X less than 1/2? Obviously not, because for individual value to be less than 1/2, all you have to do is that one number, right? But for Y4 to be less than 1/2, you are requiring for X value to be less than 1/2 at least, right? So I would say the probabilities for Y4 to be less than 1/2 is more unlikely. That is 1/4 out there, and let's call that the probability for individual value for one X to be less than 1/2. But for Y4 to be less than 1/2, you need four number. The first four number, they are all less than 1/2. So this is a much harder thing to do than having a single X value less than 1/2. So what you have is Y4, meaning that this is the number line, 1/2 is a boundary value that you got 1, 2, 3, 4. These are all random number of the X's. They all are less than 1/2. And this one is the Y4. Y4 has to be the fourth one if the data is put in order. So Y4 less than 1/2 is less likely, therefore we should have a smaller probability for this calculation. Now we know it's supposed to be small, but how do we exactly calculate it? And then I draw one situation, which basically saying it's probably for 1 to be less than 1/2 is 1/4. Now probably for 4 of them to be less than 1/2, and how likely is that? One of the common things to do is 1/4 to the power 4, right? That's 4x value. There are a couple of different ways there, because we're not talking about throwing 4 number there. We're talking about throwing 5 number there, right? 4 of them landed to be less than 1/2. So you have to consider the total number trial, right? And suppose you're throwing 10 number, having 4 of them less than 1/2 is not no big deal, right? But if you only throwing 4 number to be all 4 less than 1/2, that's even more unlikely. So we have to not only consider how many number less than 1/2, you have to consider the total number, right? If you're throwing 100 in there, having 4 of them less than 1/2, no big deal, right? There's so many, of course, it's more likely to be less than 1/2. So we have to talk about the total number trial, In this case, we got a 5 number order. So our n equal to 5, and then our p equal to 1/4. So when you think about it, this is like a binomial event. You're throwing 1x in the number line, 2x, 4x, 5x. Now you're done, and then you find out out of all the 5x value, how many of them is below 1/2. And then turns out for this probability calculation, you want 4 of them to be less than 1/2. There are 2 scenarios. Number one is 4 of them below 1/2, 1 of them above 1/2. Another situation is this. This is marking of 1/2. And then another situation, what if we have all of them? 1, 2, 3, 4, 5. Remember, we have 5 data, 5 sample points. So if all 5 below 1/2, of course, the y4, which is really the fourth one, y4 will also be lower than 1/2. Basically drawing the number line. These are the only 2 scenarios, right? Other situation that, so for example, if you get a number line here, and this is a 1/2, but for some reason you have 1 here and then the other one are over there, that's not going to be good, right? If you get 3 over here and then 2 over here, that also is not going to make the y4 a little slower than 1/2 because the y4 is going to be this one. The y4 is the fourth one, right? In this case, the y4 is higher than 1/2. And the only possible situation is this one and this one. This is having 4 out of 5, throwing 5 number there, and then 4 of them end up being less 1/2. This is P4 when the n equals 5. Total is 5, 4 of them below 1/2. This is the P5. You put in 5 number, 5 random x value, and then all 5 end up being less 1/2. So the probability calculation will be a binomial situation. You calculate P of 5, P of 4, and P of 5 for all 5 that's below 1/2. So when you're saying probability y4 less than 1/2, you will require at least 4x value below 1/2. So if you are turning the y problem into a x problem, you're actually calculating this. For y4 to be less than 1/2, we're calculating at least 4 of the x values. The random value is originally x theta, is less than 1/2. And that we mean 4 out of 5, at least 4 out of the 5x value. 5 was the total number. Trial, 5 is the total number of x values. We want at least 4 of them to total 1/2. So that sounds very much like a binomial situation, and this is how we're going to go about calculating it. Going back to the calculation part, so we can calculate probability for individual data to be lower than 1/2. That calculation gave us a 1/4. To calculate probability y4 to be less 1/2, we calculate 2 of the things using binomial formula. Binomial probability formula is 5C4. This is calculation of P4, P to the power 4 times Q. Q is the 3/4. Plus this is actually P5. That is 5C5, which is 1, and then P to the power 5, Q to the power 0. So you can see the probability is 0.0156, a much smaller probability than the probability of 1/4, because now we have a higher requirement. We want all 4, at least 4, to be below 1/2. So this is the calculation. This calculation, there are 2 things that we hope to get from here. Number 1 is understand that to study order statistics, very likely you're going to use binomial formula, binomial distribution to do your calculation. Number 2, that we actually are trying to get a common formula for probability of YR to be less than the number. For example, let's first generate the 1/2 from 1/2 to a Y. If it's not 1/2, if it's a Y value, for probability Y4 to be less than Y, right? And then the 1/4 will be switched with Y squared. The 1/4 will be switched for 1 minus Y squared. This 1/4 is also Y squared. So we have the formula at the last line. Any question? All right, so we're trying to generate that idea that is suppose is not y4 that we're talking about. So first we generate from 1/2 to the y, so we remove the 1/2 with y, and then we want to remove the y4 to yr. So what are we talking about? Any order statistics, not the fourth one, would be the third one or the fifth one, yr. All right, so in order to generate that, we're going to try to study the pattern that was displayed in this calculation. Right, so if you think about it, so for any y value, then you calculate probability of y4 would be, this is the density for y4 would be, this is the probability. It's the probability. Derivative of this cumulative probability will be the density. So we're going to find the derivative of this function. So what is the derivative of this function? It is, we have to use product rule for the first one, right? This is y2 to the power 4, and that's y8. So you have to move the a to the front and the power -1. You apply the power rule for the power part, and then multiply by this part, and then plus you're gonna keep this and then differentiate this. So according to that, we end up having this. The first two term is applying product rule. The last term is applying, this is applying the power rule for this term, and that's what we have here, right? And then we're gonna combine them. After combining them, we end up having this line. Right. There are a couple of terms that they have in common. We have this one in there, and then that one in there, and then this 4 is combined in there. We also have this one. Let's see. I think we combine some of the common factors, so then some of the terms are canceled. So this is a result after we combine the terms. So our ultimate goal is to be able to have a common formula for the density. So even though we started out studying the probability, which will be used again whenever we calculate probability related to a order statistic, but we aim to get a density function. So if you look at that density function, it has some special features. Number one, that this is a order statistics. So we are trying to get a some pattern that we can observe from the order statistics of this one. So if you're trying to figure out the density function for y4, we already know it's CDF, and the CDF is right there in the last line in this page. So this is a CDF. It's a cumulated CDF, cumulative distribution function. Now, derivative of CDF is PDF, which is a density function. So we're able to combine like term, come up with this. So the last rule is a CDF for any function that has a cumulative distribution function given. So this is this one and this one. This is a CDF for y4. So what we studied this for is that it gives us some idea how to construct the CDF for any YR. Let's try to see how what was the information in here. So if you were trying to study the PDF, which is a density function, you see what's going on. We're trying to figure out what was the behavior of y4, which supposedly is a force number in the order statistics. So because it's a force number, you'll understand there are supposed to be 2 below, 3 below. It's a force number, right? The force number has 3 numbers below it, and this one we have n equal 5. So if that's the force one, there has to be 1 above. All right, so you see the distribution. Because y4 is a force one, you have 3 below, 1 above. So right here we have a distribution. It's like throwing them all there, and then this is the force one, therefore 3 on here, 3, 1 on there. See, that 3 factorial is what's below. This 1 factorial is the one above. All right, and then this 5 factorial is our total. Rearrange everything, rearrange the number of possible arrangements if you have 5 number. Okay, so that is 5 factorial divided by 3 factorial and 1 factorial. There actually should be one more of 1 factorial. It's called trinomial coefficient. I hope that sounds familiar because you're dividing them into 3 situations. That's why we're calling it trinomial. The total number tri was 5. So among 5, you have 1, 2, 3. Now the one in the middle is the y4. Because there's only one number, you try to permutate 1. 1 factorial is 1, right? And then, so that's the y4. So you have that trinomial coefficient there. It's just following the distribution on the number line. And then this is one that's below y4. So this you have to use a probability that there are 4 of them below the y4. So this is actually P4. So you have, this is below call that Py, they're below the y value. So probability for any value to be below y is y. There's 3 of them, so this is to the power of 3. And that's why there's a cumulative distribution function to the power of 3. And this is a probability that out of the whole 5 number, 3 of them below the y. All right, and then there, this is the probability for one of them above the y. That's 1 minus f of y. F of y is a cumulative distribution function, therefore it's a probability. So f of y is a probability, but f of y is a probability to be below. If you want to find a probability above the y, that's 1 minus f of y. Right? And then so that's the one below, and then over here you have the one above. It goes 1 minus f of y. And then right in the middle, right, you have the number is at the y. So the y4 is this is density function. Y4 is at the y. So in that case, you should have your density function, not the cumulative distribution function. In that case, that's actually a derivative value. So it's a point behavior rather than the interval behavior. To be above or below is an interval. So you're putting the probability for the interval. But right at that point is the derivative for the amplified. So that's really for the middle point there at point 4. So this is really my interpretation to get a understanding of it. So we try to go from there and then have the formula for how do we like generate the idea that we learned from the example to any density function. So which end up getting us this, right? So this is the probability density function for a YR. That is, if you are trying to find out the density function for the first one, the second one, the third one, or the fourth one, the R can be any number from 1 to n. So, and you can see this is similar to the one we already had earlier. If it's not the fourth one, if it's the R's one, how does it work out? If you think about the reason for how this works out. The book actually derived the whole thing, but this, we can look at it from this standpoint. So this is really the YR, the R's number in the order statistics, and this is a Y value. Okay, so we're saying probability for YR to be at Y. I mean, Y is a value of the order statistics. And then the R is that YR, with a variable. Okay, so having the YR equal to Y means that you have to have 1 minus R. I mean, we can't really mark out how many since we don't have numbers. How many below the Y? There has to be 1 minus R of them. So in this case, you have to have the f of Y probability to be below the Y to the power of not 1 minus R minus 1. YR is the R's one to the power R minus 1. And how many of them above the R, that there has to be n minus R, because the total number is R of them. There's 1 in the middle, so R minus 1 to the left, and n minus R to the right, and there's 1 here. So n minus R plus R minus 1 plus 1 is the n, right? The total number is n. So we have the 1 minus f of y, which is probability to be above this y value on the number line, 1 minus f of y. This raised to the power of n minus r. And right in the middle, this one, you have to multiply the density function. So that kind of explains all the factors in multiplication. And you can think of this kind of like a trinomial situation. And then over here, what is number 4 is to give you how many different ways for this to play out. For example, there's supposed to be r minus 1 of them below the y, but they could be a, b, c, d, b, c, a, d. So all the r minus 1 of them can't have a rearrangement. That's why there's an r minus 1 factorial there. And not there are n minus r. Sometimes n minus r ends up being 0 or 1, but sometimes you may have multiple terms there. And then this n minus r can be rearranged, and that's why we have that division there. That's how we can lay out. The numerator n factorial is really how many possible rearrangement for n items. Okay, so that kind of explains part of the reasoning for how do you set up the density function for the YR, the order statistics. We do have some derivation before this page to explain how do we generalize it. Because after all, this exercise work on deriving the density function for Y4. So how do we generalize that? So we assume that we have an order statistic, assuming that we have a cumulative distribution of capital F, assuming that we have a density function of lowercase f. I guess I'm missing one there. It's the derivative. So derivative of capital F is a lowercase f. That's the density function. And also f of x, the capital F, should be an increasing function. I mean, cumulative means it accumulated, so it's always increase. It increases from 0 to 1. Capital F of x is a probability. So any probability has to be between 0 and 1 because it's increasing. So f of x increases from 0 to 1. Now we want to know is to talk about what is the behavior of YR, and the YR is representing the R order statistics. And then, so we want to find out what was the probability that YR is less than Y. We start with this, and then we're going to try to find the derivative of the CDF. So what we're going to do is similar to what we have for Y4. When we try to study probability Y4 is less than 1/2, we started out with what is probability YR is less than Y? Okay, so you can see a big summation there. I don't know if it makes sense to explain, but I feel like you can see the reasoning why we have this formula. It's still follow the binomial distribution that we had earlier when we want to come up with the formula for how to construct this function. So this is a derivation of probability YR less than Y. All right, so if you have YR less than Y, what does it mean? So this is a Y value. And to have YR less than Y, there are a couple of different situations. Number one is you have R of them below the Y, and then you have N minus R number among the N number is below the Y, and then N minus R is above the Y. So that would be the PR, right? If you're able to have the density function and this cumulative distribution function. Another situation is R plus 1. That's you have R plus 1 below the Y, right? If R plus 1 of them already below the Y, of course the YR will be below the Y. So basically we go with the idea of YR below the Y, meaning that at least R of the X value has to be below the Y value, right? So what does it mean by at least R of them? And that including P of R plus 1, and 2 all the way to P of N. So here I'm just trying to explain why we get that formula from. So really we're calculating in a binomial distribution with an n equal to the number of trial, the p equal to the cumulative distribution function. We're calculating all this. We can actually follow the binomial distribution for each calculation. For example, let's say k equal to one of the index. So we were calculating a binomial distribution npk. So for example, the first one will be NCR. fy to the power r and then 1 minus y to the n minus r. This is really what right here is a binomial distribution following each of these probability calculations. Any question? All right, but our ultimate goal is not to calculate the cumulative distribution function. As you can see, it's a big summation because we don't know the r. Therefore, we don't know how many we're adding. We know that r is less than n, depending on the r value. But we want to have a function, a formula that does not have the sigma sign. And sigma sign has the unstable factor in there. There's a lot of indeterminate case in the. So we want to have a common formula for the density function. So we're going to go ahead and find the derivative. Derivative is the derivative is a density function, and in order to make the derivative calculation easier, we're separating this into this. All right. So why are we separating into that format? Because when you look at this first format, there's multiplication involved. The multiplication there is because the binomial distribution formula, right? There's a multiplication, but we can separate them. If you look at the first one, I think with n, okay, when the k equal to n, then we have NCn, and this is a power n, this is n minus n, which is 0, and that one, okay? So when that's the highest term, the last term, right? That's the p of n, like this one. This one does not have multiplication, right? Because it's really p to the power n, NCn, p to the power n, q to the power 0. So to get rid of that q part, so there's no multiplication. But all the other one, when the k is smaller than n, we have this one and that one. So that means we have to apply product rule for the differentiation. That's why we separate them. So after separating them, we will find the derivative. So when you try to differentiate the first part of the summation, you have to apply product rule. And so that's why there's a summation here. The summation, when you apply the summation, this is the NCK, which is already here. But when you're differentiating this part, you have this derivative, right? And then according to product rule, we'll start differentiating this part. And then according to product rule, we have this. But to move the n minus k to the front, n minus k minus 1, and then this. Because we are differentiating the cumulative distribution function, not only do you have to move the n over k to the front minus power, you also have to differentiate the inside derivative of the f of x, capital F is a lowercase f. That's why we have that extra part. So with that one, if you differentiate it, you have that extra f over y right there. So this so far is the calculation for the big summation part. Now, then you have to add, when you differentiate this, it's going to be n f of y to the power of n minus 1 multiplied by f of y. After all, we are trying to find the derivative, right? Capital F derivative is lowercase f. And that's really what we derive here. That's what we end up having this. There's just trying to make the differentiation streamlined. And then we see a lot of things that we can observe that is, and you can see they all have f of y minus fy. They have, what I'm trying to say, this is a telescoping theory. Many of the terms end up canceling each other out of the summation. So even though we are adding a lot of things in here, if you derive it, I see this is NCK, n factorial over k factorial times n minus k factorial, and then the k cancel the k factorial in the denominator, so they will be able to cancel one of them. I think there are a couple of terms will cancel. This one will also cancel the n minus k. In this one, the denominator has n minus k factorial. So there are some terms that are canceled. They end up having identical terms. And then, let's see. So if we cancel some of the term in the summation, and you see NCP times K equal to this, and then NCP times N minus K this. Okay, so we are able to cancel some of the common factor, which is the big summation and the second summation. The first two summation after cancel a common term, there's only one term left. Which one's left? I think it's this one. One of the terms, the first term is the only term left. All the other one was canceled because of following subtraction term. There's a line inside there. Any question? All right. So what it does at this part is giving us a common way to derive the density function for any YR. So we already had that YR, GRY is the density function for YR. So like I said, this is the R's value in the order statistics. You have R minus 1 below the R's term. You have N minus R term that's above the R's term, or the YR of the statistic. So the R minus 1 should be the power of Fy, and then N minus R should be the power of 1 minus Fy. And then you multiply by the density function. Following that, for example, if R equal to 1, and this R equal to 1 minus 1 is 0 factorial, 0 factorial equal to 1. This is N factorial, N minus 1 factorial, N factorial divided by N minus 1 total equal to N. So there's an N. And this is the R equal to 1 minus 1 equal to 0, so that Fy is gone. 1 minus y to the N minus 1 power times Fy. So that kind of give you the density function for Gy, G1y, and if you want to find the Gny, that's when this one equal to N, and R equal to N, so N minus R equal to 1, N minus R factorial equal to 1. So this one over this one equal to N, and then everything will follow the formula here. Basically, the second rule, GRY, would be kind of like a common formula for the density function of YR. I hope that can make sense. We don't always use the density function for YR to do calculation, but sometimes we do write it out just to compare the behavior. All right, another way to construct GRY is to go by the differential. So you can think of the GRY as the height of the area below the density curve. So the GRY multiplied by delta y should be the area below the little orange part in the graph. So that should be the probability that YR is between y and y plus delta y. So in here, as long as we can figure out a way to calculate this probability, then we will be able to calculate the GRY. Basically, the left and right side of the first rule is the overall idea. You're going to focus on how to calculate the right side probability. So how do we calculate probability YR between these two? First is probability for individual number to be below that of the y value is Fy. That's really the CDF. So for probability for x to be above the y plus delta y would be 1 minus f of y plus delta y. So really we're identifying the, let me try to copy this so we can write on top of it. I mean, all we are doing is just trying to figure out how this can make sense. So basically, we know this equal to this because this is a height. If we think of this as height or individually, then these two, the height is this, all right? And the waist is a delta y. So the height times the waist should equal to the orange area, right? So the orange area also should equal the probability for YR, which is the variable to be between the y and y plus delta y, right? And so as long as we can figure out a way to calculate this, we'll be fine. Or another way to think of it, as long as we can figure out a way to calculate the color part, we're fine. So what we do is we end up trying to calculate what's on the left. So what is the probability to below y, which is this part, And how do we calculate probability below y? We have that formula, f of y, right? Probability x below y. Now, probability for anything between the y, it's 1 minus the capital F, and that value is y plus delta y. Right there. So if you want to find probability to be between these two, all you have to do is to subtract out of 1. So you have right, I was thinking about combining this one and this one, which is this one. Basically, you add this to and subtract out of 1, right? And then it's going to be 1 minus f of y, and then minus 1 minus f of y plus delta y. All right, and then canceling the y, you have f of y plus delta y minus f of y. Right, and that is equal to what we have here, equal to the density function of f of y multiplied by delta y. And that gives us each of these components. It's this one. All right, so basically to construct this calculation, we'll have all three multiplied to this one, and this one. That's really the probability constructed using the multinomial probability formula, or trinomial formula, trinomial probability formula. Right. Any questions? Right. Below we have that picture that I was trying to study or trying to figure out some pattern in how to determine the density function for YR. So there's a couple examples in the section. We can try to find out. Suppose we already have an example. Y1, Y2, Y3, Y4, Y5, and we can study the density function for all 5 of them according to this formula that we have here. This one, second one. We can construct Y1R, G1R, G2R, G3, G5, G5, right? Using the formula we have over here. With our R being 1, 2, 3, 4, 5, able to construct each one of these. And then we can use this as integration. So if you integrate every one of these formula from 1 to 1, multiplied by y, you'll be able to find the mean. The mean value for y1 is as you can see, the number is getting bigger and bigger. Because these are average value for the older statistics. Average value for y1, average value for y2, average value for y3, y4, and y5. So using each of their density function, we can determine their average. Are we on time? I'm sorry, so it's over time. Sorry, that's it for today. Thank you. Sorry.